You want to detect a pothole. Think of these hidden layer neurons as some junior analysts who are working, and one person is just looking at a round patch. The other person is looking for surface cracks, another is looking for debris, another is looking for depth, leaks, things like that, right? And then they go to the hidden layer 2, which is like their manager. And he says, yeah, I found 0.5 chance of a round patch plus 0.6 chance of a surface crack. Then some activation function in this layer clicks, right? And same thing, this manager is looking for leaks and depths and something else. And then they go back to their boss and say that, okay, based on my activation function is yes, and this person says mine is no. And then let's say the boss has some overall weightage of this manager's activation function 0.5 plus this or 0.5. Based on that, they say, yeah, this is a priority, we need to go and fix it. This is how a neural network would look if people were doing this individual task. Except in traditional machine learning, like this round patch, surface crack, we call them features. So we create different features and then we run a machine learning algorithm. As opposed to in deep learning, these features are figured out within the network itself. So while I'm calling out this as a round patch, we don't really know which of those neurons correlate to a round patch versus a surface crack. Some of those do, and then we go get the answer.
It's pretty simple. If you can actually illustrate an equation, you're machine learning. If you can't illustrate the equation, you're deep learning. And so it is really about knowing your inputs, your outputs, your variables, and the different pathways that you've actually structured to get to machine learning. Whereas deep learning is, hey, give me the data and I'll tell you what I tell you. The opacity of deep learning models is one of the reasons why the medical industry was really hesitant to use them.
I was doing square roots with my 10-year-old daughter. So what is the square root of 256, right? And she doesn't know. She doesn't know all these tables beyond 10 or something, right? And then one of the ways is like, you try like, what is the square of 5? 25. Okay, so it needs to be a number that is bigger than that. Let's try 10, 100. We are still not close to 256. Let's try 20, 400. Okay, that's too big. So we need to come down now. We went from 5 to 10, and then 10 to 20, and then we said, let's try 18. And then you come down and then you find. Right? Like when a mathematician is solving a problem, they are using an equation. When a computer scientist is solving a problem, they will say, I will just try to approximate based on is the loss in the negative direction or positive direction. And based on that, I will change my weights. And then I will see how far am I from the loss, and based on that, I will take a step. So those are the ideas behind backpropagation on how do you get the feedback and how do you move towards that approximate solution. And then in this case, you'll get the exact number for 256. But if you have like multiple variables and multiple combinations, you would never get an exact answer, but you'll get a close enough answer with 99% accuracy. You can tell whether it's a cancerous cell or not. Like that's the intuition behind how the learning works behind this.
My sister is a neuroscientist, and she actually has her PhD. She actually did a lot of studies on brain scans, essentially for people who have had concussions, and looked at the damage to specifically the neural pathways that come from concussions. And she did a lot of the snappings. She also did it in a computer science lab. So when we were talking, she would actually explain a lot of how neuroscience shows up in my work, which I thought was fascinating. And so we've actually found a lot of common ground.
This is a continuum of our modeling, where initially we started with some business rules, and then we proved or disproved some business rules. And based on that, we said, well, why don't we just throw in that whole data and let the traditional statistical approaches and machine learning approaches figure equations out on their own. And then we talked about ensemble learning, where we said, well, each approach is good at one. So what if we mix these approaches, like the Netflix challenge, and then a combined approach, which is getting less and less interpretable. Like one machine learning model is clear to understand, but now you add 5 machine learning models and take an average of their output or something. Now it's slightly getting less and less interpretable, but better. That is the one that won the Netflix challenge, so it's getting better. Neural network is further down on that. Like it's getting even less interpretable now, but even better at performing. And then LLMs take it like foundational models. It's trained on some data like in a completely different context. You're bringing it in, even less interpretable, right? And even higher performing.
Welcome to govai.fm, your no-nonsense guide to AI in the public sector. Connect with peers and learn from real successes, failures, and lessons from the trenches.
Think of it as like 5 R&D AI labs, which kind of grew in parallel over the last half of the century. And they had different assumptions based on which they wanted to solve this AI problem on how machines can think. Symbolists treat learning like finding rules, discover crisp if-then-else statements to explain the data. So Bayesians were about learning everything with probability lens. And then there were the analogizers. Their worldview was that learning is like by analogy. So if you identify anything that resembles the other, then you can predict the thing that you're wanting to predict. The fourth is the evolutionaries. So they said, all our intelligence came based on evolution, right? So borrow something from Darwin, generate a lot of candidate programs, a lot of candidate hypotheses, and then crossbreed and mutate. And then the fifth were the connectionists. The current state of AI and the things that are very popular come from this approach. So the connectionists imitate the brain. What they said is, well, we know something that is intelligent, something that does intelligence, so let's try to copy it.
So this is part 2. We did part 1, and this is just a follow-up to make sure that we're retrenching ourselves in what we had done before, just so people get a chance to really understand what AI is. And this is just the basics around what AI is. And once we do that conversation, it's going to be a lot broader in terms of how we're using AI and talking to people in the industry and really moving the conversation forward.
Absolutely. The next part of the story is the neural networks. There was one group who took inspiration from the brain and how a human brain works. And that group was working in the background and things weren't quite going their way. Like in the 80s, 90s, even early 2000s, people like Jeff Hinton, who is here, continued to make progress on it. So on the top, you have a neuron, right? Like, so in the neuron, all these hairy things on the left hand side, those are dendrites where a signal comes in from the left and the neuron makes some calculation and then sends a signal forward to the next neuron. And that's how our brain functions. And that's how we learn. That's how we take actions.
So I want to step in here just a little bit. I don't know if you know this, Girish. My sister is a neuroscientist and she actually has her PhD. She actually did a lot of studies on brain scans, essentially for people who have had concussions, and looked at the damage to specifically the neural pathways that come from concussions. And she did a lot of this mapping. So when I talked to her, she also did it in a computer science lab. So when we were talking, she would actually explain a lot of how neuroscience shows up in my work, which I thought was fascinating. And so we've actually found a lot of common ground talking about different neural networks and how they actually mimic how our brain makes connections specifically, and how, a lot of our dendrites burn off by the time we're 25, right? So basically, because we have brain plasticity when we're younger, it ends up creating much more flexible pathways in learning when you're younger than when you're older, because your brain actually shows you get set in your ways.
Totally.
However, when you have computers, they're not going to get set in their
Yeah,
ways.
they'll keep learning. Absolutely. So the thing below is just a simple neuron, which was made in 1950s, right? Like it takes in all, like in this case, we are talking about the example of a building size. And based on that, we want to know how much HVAC, like how much cost there is to heat up the room, right? Like, so age of the building, size of the building, solar exposure, all these, you go into a neuron and some activation, you create some sort of a weight. So size times 3 plus age times this minus solar exposure, something like that happens and an output comes. So that's just one neuron, right? This tribe had this intuition that what if we just build a lot of these neurons, make a network of it, and somehow we'll figure out some way to have that network learn, and that would be our algorithm.
So
And
is that fair, though, to say that they had this intuition out of somewhere? Did they not just think that, well, the human brain has a crap ton of these, so why don't we just mimic the human brain and see what happens? Like, that to me feels more
obvious,
hot. Yeah, like the hypothesis a scientist would make would be like, hey, let's model
this
this after the
works.
brain and see what works or see what happens.
This wouldn't have been mine. And I'll tell you why. Leonardo da Vinci, where he was trying to make a flying machine, and he had this flapping mechanism. Just because nature made a flapping mechanism that birds used to fly doesn't mean that that's going to work, right? Like evolution necessarily is not the most optimal, right? Like aeroplane has a totally different technology.
Yeah, I mean, we are
Yeah.
accidents. We're biological accidents of natures, and we are definitely
Yeah.
not perfect. But I would think if you're actually
Yeah.
modeling this after your neurons and your neural pathways, that you would think, like
In
let's
theory, it
do
should
what
work.
yeah, like the brain might be something we should replicate.
Yeah, totally. So that was the intuition of this group. And basically what they did is they said, well, this is just one neuron, but what if we just line up a bunch of neurons, give them some inputs, give them some outputs? We still need to know how it learns, right? Like this is just mapping inputs to outputs. So we need to figure out if the output is wrong. Like when a baby is learning, we know how the neurons go forward. We don't exactly know how that learning happens, right? Like we don't know when a baby first time touches fire, the next time what happens in her neural pathways, what weights change in their neural pathways, that the baby is not going to go close to something hard. So when you give a feedback to this network, for example, which of these weights should change? Like that was one big problem that Hinton and the group were trying to solve. But before solving that problem, they said, in theory, if we could learn, then what can happen? There is something called universal approximation theorem. So based on any inputs that you have, like in this case, it's like age and blood pressure, for example, just with two variables, it can get complex. So if you had hundreds of these variables, then the input to output mapping gets very complex. So some of the initial algorithms that we thought of, like linear regression, where we said age of the building times 3 plus this times 4, those are linear equations. They cannot model some of the very complex patterns from
I
input.
know.
Yeah,
Nuance is so important in variables, right? So it
certainly.
basically creates an ever increasing complex model as you add more data.
Exactly. And earlier, some of the earlier ways, like the statistical way, the tree based way, they take care of some of these variables and they model it in a specific way, like the tree. And those ways are very interpretable. So we know why we made a tree of decisions, like a decision tree. We know why we did it. While this is not interpretable, the universal approximation theorem says that like if you have just one layer of these neurons, and a non-linearity, which we'll come to later, but just a simple neural network can approximate any function, any complex function, which any like a regular algorithm cannot approximate. This can arbitrarily approximate anything. So that's the power of this neural network. Basically, it can learn anything. It has the capacity to learn anything.
It can, but it doesn't have the capacity for nuance yet at this point that we're sharing, right?
It can doesn't mean that it will, right? And
Yep.
that's what, yeah, that's what we will go into next. And this is an example in a public sector company, right? Like, so you want to detect a pothole, and then there are think of these hidden layer neurons as like some junior analysts who are working, and one person is just looking at a round patch, like I'm just looking for round patches, and the other person is looking for surface cracks, another is looking for debris, another is looking for depth, leaks, things like that, right? And then they go to the hidden layer 2, which is like their manager, things like that, right? And he says, yeah, I found 0.5 chance of a round patch plus zero 0.6 chance of a surface crack. Then something ticks, like some activation function in this layer clicks, right? And same thing, like this manager is looking for leaks and depths and something else. And then they go back to their boss and say that, okay, based on like my activation function is yes, and this person says mine is no. And then let's say the boss has some overall weightage of this manager's activation function 0.5 plus this or 0.5. Based on that, they say, yeah, this is a priority. We need to go and fix it. Right. Like, so this is how a neural network would look if people were doing this individual task, except in traditional machine learning, like this round patch, surface crack, we call them features. So we create different features and then we run a machine learning algorithm. As opposed to in deep learning, these features are figured out within the network itself. So while I'm calling out this as a round patch, we don't really know which of those neurons correlate to a round patch versus a surface crack. Some of those do, and then we go get the answer.
And deep learning actually takes a lot more training and a lot more data, and it has to be a predefined model when you're actually doing it, right? So as you're building these machine learning at the first layer, if you are actually defining these features, that takes a lot less effort. That takes a lot less effort. If you're
Totally.
doing deep learning, you actually have to educate and train your model in order to do deep learning.
Yeah, very good point. Just because it's so powerful, that means that it can go wrong in so many ways. So you need to really know how to train a deep learning model.
Yep.
The next question is, how does this deep learning solve the learning problem? Many of the traditional machine learning problems, they have an exact mathematical equation. Like,
Right? Like it's pretty simple. If you can actually illustrate an equation, you're machine learning. If you can't illustrate the equation, you're deep learning. And so it is really about knowing your inputs, your outputs, your variables, and the different pathways that you've actually structured to get to machine learning. Whereas deep learning is, hey, give me the data and I'll tell you what I tell you. The opacity of deep learning models is one of the reasons why the medical industry was really hesitant to use them. I'll tell you a story. So I was talking to my sister, and she told me that an x ray predicted with 99.7% accuracy when a patient had a specific type of cancer, except they could not use the deep learning model because they couldn't explain why the deep
why?
learning model was selecting those patients as having cancerous cells. Now, the interesting thing about this is doctors were at about an 80% accuracy rate, right? So they were missing about 20% of the people who actually had cancer. But now there is a drive to move towards creating, Girish and I kind of refer to as white box AI to help with these things because what actually matters in, let's say, that scenario specifically is the diagnosis itself. It's the ability to treat and treat early and identify, right? So, if machine learning or if a deep learning model is more accurate and can predict if someone has cancer, and if you're wrong 0.3% of the time versus 20% of the time, that's something to consider as we look at the variables of how we actually approach addressing certain things. But where we are wrong 0.3% of the time, that can cause a lot of heartache. It can cause a lot of mental anguish. But so
Totally.
does that
Yeah.
20% that we've left out, right?
And the same like in medical, it's like auto driving cars. If like number of people who cause accidents versus an auto driving car causing an accident, so there is that the same issue you see in many different places.
Yep. And this is when we start thinking about, okay, the variability. And for me, this is when we're going to get into ethics later on in our series, but this is where the ethics come into play around AI,
Totally.
right? Does it affect decisions around people? Does it matter in terms of how it impacts their ability to access services? Is it increasing the privilege of some while denying accessibility or services to others?
The question is like how do they learn? And one of the intuitions for that learning on how this approximate learning happens is because we need to learn the weights. And on the left hand side, while there is a formula, the problem is if you have a lot of data, you cannot invert that matrix anymore. You'll just need too big a RAM to invert that matrix. Like you'll have a lot of problems dealing with solving these equations. It was a loss function. One of the intuitions that like I was just thinking of was when I was doing square roots with my daughter, 10-year-old daughter.
Wait, she's doing square roots in Montessori?
So what is the square root of 256, right? And she doesn't know, right? Like she doesn't know all these tables beyond like 10 or something, right? And then one of the ways is like you try like what is the square of 5? 25. Okay, so it needs to be a number that is bigger than that. Let's try 10. 100. We are still not close to 256. Let's try 20. 400. Okay, that's too big. So we need to be come down now, right? Like we went from 5 to 10 and then 10 to 20 and then we said let's try 18 and then you come down and then you find it, right? Like so when you're solving the like when a mathematician is solving a problem, they're using an equation. When a computer scientist is solving a problem, they will say I will just try to approximate based on where like is the loss in the negative direction or positive direction, and based on that I will change my weights, and then I will see how far am I from the loss, and based on that I will take a step. So those are the ideas behind back propagation on how do you get the feedback and how do you move towards that approximate solution. And then in this case, you'll get the exact number for 256. But if you have like multiple variables and multiple combinations, you would never get an exact answer, but you'll get a close enough answer with 99% accuracy. You can tell whether it's a cancerous cell or not, right?
Yeah.
So that's how this is working. Like that's the intuition behind how the learning works behind this. And this all came pretty recently. Like so since 1950s, people have been figuring out neurons and all. 85 is when Hinton and the group, like 1985, that was still a long time ago, right? Like, but still it took a long time for them to reach the ImageNet, right? ImageNet is this competition where you are trying to figure out what image it is based on the pixels, right? So the input data is the different pixels, right? And earlier, a lot of traditional machine learning algorithms were used figuring out each different data and giving that as an input, creating some features, like I was talking about, like those pothole related features and all, and then coming up with an answer. And then, so there were like 1,000 object classes, 1.2 examples
I
of trained
remember
images.
this. I remember this, and I remember when it came out and how excited people were about this. It
Yeah.
was such a big deal.
And a lot of traditional machine learning were being used for this
Yep.
until like, and then the error rate was like 28%, like in 2010, right? Like, so
Yep.
2008 it was much more, and then error rate 26%. And then 2012, some of Hinton and his students got it like to jump from 26% to 16%. Like that never happened. Like something really foundationally has changed in machine learning there, right? And then
Think about this. So, in the first 2 years, there was a drop of 12%, right? In the next 2 years, there was a drop of 10%. And then the next 2 years or 3 years after that, it was 4%. But if you look at this on a per percentage basis, you're looking at an over 50% reduction rate in errors,
I know, yeah, it's
right?
crazy. Yeah, yeah,
Like, that's insane. Well,
yeah.
60% actually, if you're doing the
So
math
yeah,
correctly. Yeah, like, and when you think about the fact that these algorithms that are built out, these neural networks that we're training, they learn from the data that they're getting, and they are self-learning, right? So essentially, they don't stop. We stop. We need sleep. We need to eat. We shut our brains off. They don't stop.
And the data scientist job becomes easy. Earlier, we used to do this feature engineering and figuring out features and all. And here, no, you just throw the data, you just get the right kind of a network. The more data you throw, the better it gets. That's it, right?
Yep.
So the next like 20, like AlexNet happened where these were Hinton students, and then they said, like, what just happened? Next year, everybody used deep learning. They kept all their other machine learning things on the side. Everybody 11%. The year after that 6.7%. Humans was 5%. Like even humans cannot exactly tell some of these things. So human accuracy was 5%. But 2015 the contest stopped because it was solved, right? Like the problem was solved.
And also, we just figured out that computers got smarter than humans, and humans don't like that.
Maybe that's why.
They're like, nope, we're done. We're feeling dumb. We don't need this anymore.
At that time, like this was a cool time though, right? Like 2014, 15, everybody's like, and this was
Yeah.
all just in computer vision. Like text hadn't come in, mind you. The same thing
Yep.
is going to happen in text in the next few years. If we are in 2014, so far computer vision, it's huge, right? In fact, when I was doing like that's when I went back to Stanford and I was doing the Stanford work, and I remember like some of the VCs, like when these were just students, right? And we did a project on something in computer vision, like some silly project where you can take a picture of a food and then tell what calories it is. Didn't quite work, but some people tried to do it, right? And people were wanting to put money on it, right? Like just because there was like a big explosion of like, wow, this can learn anything. This is what started happening. The more and more data you put in, the traditional machine algorithms, they plateaued. They couldn't get better. Like accuracy 70, 80, 85, and then 85.5, 85.6, because there was no universal approximation. So they couldn't find any detailed patterns that are in the data and all, you couldn't find, right? But the deep learning model kept getting better and better, like auto-driving cars.
Machine learning is limited by parameters that you put in. It's limited by how the algorithm is developed and built and what you say to it, because it is fully transparent. Whereas deep learning, you're like, go figure it out. And it figures it out.
I know. And this was the magic. So one of the things where it really outshined, like machine learning, mind you, was still used at this time, right? Like 2014, 15, like when I was solving problems, I would start with some of the basic models. And I would also end with some of the basic models.
To be fair, you still use machine learning, Girish. Like there's utility for it, right?
Totally. Yeah. Absolutely, there is. And we'll find ways of combining the best of both worlds in the upcoming slides. But one of the places where deep learning totally outperformed is in, remember, we were talking about system one versus system two thinking. So all the system one thinking tasks, like computer vision, or listening to a voice and translating it into something, right? Like voice to text, text to voice, like anywhere where there was unstructured data, this was like easily outperforming. Like you wouldn't even think twice before going to deep learning for those things. And so there is actually an interesting story here. So we talked about Hinton, right? So this is about Yan LeCun, another hero. Now he works at Facebook, but he came up with one of the networks based on this deep learning to identify digits and then identify, on your check, like identify what the check is for, and it automatically reads it. Like it was deployed in 1995, right? And one of the architectures with deep learning, convolution neural network. And there was a fascinating story. He was working at Bell Labs when he came up with this, and then in 1995 it was deployed, and then Bell Labs split into Lucent and the other one. I forgot the other one. Then his patent went to the other company, so he couldn't use it till 2006 or 7, like from 1995 to 6 or 7, when actually the time of the patent was over. And in the meantime, the other company was not even aware of convolution neural network was like one of the top things, but they were just sitting on it from 95 to 2006.
And they had no idea, and they didn't renew the patent, because you can renew patents, right? And so
I guess.
they didn't renew the patent. I was working at the banks, and so as we know, the iPhone launched in 2007, and that actually basically changed the whole landscape of how people interact, how they talk, how they engage socially, right? But it also changed the business landscape. So you ended up having a whole bunch of mobile stuff. But as we started getting into mobile, one of the biggest hurdles for customers in banking was, well, I don't want to have to physically take my check into an ATM and then deposit it. And they used this technology to do digital check deposits, right? That's what
Yeah,
this
totally.
actually is used for in an application perspective in the world today. And now we're using it for digital identity verification. We're using it for so many different things. So maybe it happened in 2006, it became available. It was created in, when did you say? 19?
95, it was used. So 90s, early 90s, it was created by
So it was
Jan LeCoux.
created in 95. So let's think about this timeline. Created in 95. It was then patented and kind of hidden where people didn't know what they had. 2006, the patent expires. 2007, the iPhone launches. Between 2010 and 2012, the iPhone mobile app environment explodes. 2000, I think it was maybe 13 or 14, like the whole the check image depositing came into play. And basically, as we go into the 2020s, digital identity verification is happening now. So think about the length of time. That's 30 years since this technology was designed, right? 30 years since this tech was
Yeah.
designed. And that's how long it takes to actually come to fruition. So now let's think about we're going to get there. Like let's think about LLMs and where they are today. Like we're just seeing the baby phase, man. Like where this is going to go in 30 years. I mean, that's something to think about.
Yeah, that there are voices on both sides, but this was like an architecture is beautiful here. Like the convolution, the idea is that when you're looking at digits or something, you look at the pixels next to each other and form some pattern, and then those pixels next to the other pixels form bigger patterns, and then you say, oh, it's a circle, and then you say, oh, it's an eye, right? Like so, that was the idea. But it was a very beautiful architecture, and even now, like one of my favorite architecture. Even though right now everybody is using transformer architecture, this was one of the top architectures that came out in deep learning.
Let's make this real for people. It's a puzzle. So when you pull out puzzle pieces and you have to put these little pieces together to create the bigger picture and whole, that's what this is showing you. It's actually showing
Exactly.
you that it's taking little tiny pieces of the image and then creating and learning the context of that specific image based on what it's seeing in these little puzzle pieces that are coming through.
In a jigsaw, in a
Yep.
jigsaw kind of a format. Yeah, absolutely. So that's what it's doing. So these are the grandmasters of the modern deep learning and the tribe that we are talking about. So Jeff Hinton here in the middle, and then on the right hand side is Jan LeCoux, the CNN guy, and then Yoshi Abengio. And Aman, you have met him, right? Like
Um,
Mila.
Well, I haven't quite met him yet. I'm looking forward to it. I'm actually engaging with Mila on a few things, but he's been presenting at a number of conferences I've been to. And frankly, he's a phenomenal leader and he's actually done a lot for the research space in AI in like especially UDM, right? So University de Montreal, Mila's connected and they're actually doing a lot to develop talent and students and they're working with public sector entities there and oh my God, I can't say enough. The other thing they're doing, which I think is fascinating, is they're allowing you to access talent from universities like professors and PhD students and master students, specifically to create open source solutions, which are then widely accessible to other public sector entities. And they're the arbiter, right? So they're actually sharing all of the work that's being done with people who can use it, which I think is, like I mentioned before, the path to good AI. It's just a really cool model. And I don't think anybody, unless you're like a super nerd who lives, breathes, and eats AI, the government of Canada about 2 years ago, maybe a year ago, announced that they would be releasing $2.5 billion to build our own data center so we can actually build our own models. Now, to put that in context, $2.5 billion is actually nothing. It's a drop in the bucket when it comes to AI.
Yeah.
When you look at what Amazon announced, the same kind of couple of weeks after, Amazon announced 38 billion, 10 different data centers. They announced this huge investment into their AI infrastructure. So that tells you, like, as government entities, there's a lot less to go around, but people are trying to make do with what they have, and the talent is attracted. So Joshua Bengio was attracted to doing good and creating a institute that supports AI for public good. It's not that they don't support private entities. They do charge them an arm and a leg, though, so they make money on that to support the open source work. So I think this is such a better model. Anyways, I just wanted to
Totally.
talk a bit about the work they were
No,
doing because it's been
absolutely. Yeah, I wanted
fascinating.
to. Yeah. So they got the Turing Award. Remember we talked about Turing and the Turing test. So 2019, the three of them got a joint Turing Award, and I mentioned Pearl, Udaya Pearl, and he got it in 2011. But yeah, so they got the award for this work. But the real fun started not just in how it learns and how you keep throwing data at it, but what it did was it could do transfer learning. So some of these initial layers, which if you train on potholes, then they are identifying some shapes and circles and this and that. If you take those initial layers and then just apply a new layer to do something else, like medical imaging, for example, then all the things that it learns on how to figure out shapes and all is still useful.
I,
You
I
can use
think
all of
this
that
is a
network.
But think about how humans learn, right? So at first, when we go to school, we generically learn our basics, our foundations. As we go and increase our learning through high school, post secondary, and then if we get postgraduate, right? If we go undergrad and then postgrad, and we actually start looking at everything in that space. What I find interesting about this is when you think about what a PhD actually is, a PhD is not someone who knows everything about everything. A PhD is someone who takes this bubble of knowledge and then just kind of ekes out an additional edge of more knowledge that adds to that bubble of knowledge. So they become very, very specialized in proving out something that's theoretical or actually supporting a thesis or a theory that's going to help increase human knowledge overall. But they don't know everything about everything in every space. And I find it so fascinating that people think PhDs are smart in everything. Like, I love PhDs, don't get me wrong. My sister is one. But it is really about they base their foundational knowledge on common human knowledge, and then they learn and add to human knowledge. And that's exactly what these models do, is you seed them with base foundational knowledge, and then they learn on top of that on the things that they are being trained for, the additional data they're being given.
Yeah, this is fascinating. So when I was doing, so this was 2017, and I was doing like deep learning and natural language processing course. And in our course, one of the questions was you get a paragraph, and based on that, you answer some questions, right? Like automatically answer some questions. And at that time, these transfer learning foundational models, like Aman was saying, were started. So BERT was the popular model, which is equivalent to the GPT-2 equivalent models. And at that time, we had a leaderboard on who wins, like who gets the most accuracy in answering
I don't
questions.
know why you got to make it competitive. I don't like the competitiveness. Like, why can't we
You
just
got
all work
grades based
towards a
on
goal?
you got grades based on like how you were on the leaderboard, on how
I know,
accuracy
but
was 82% and that kind of stuff.
I
Well,
don't
in
like
addition
that.
to I know, but in addition to the novelty in your approach and all, but one of the things was we had two leaderboards. So one was the leaderboard of people who were using foundational models like BERT and all, and one was the leaderboard of people who were not using foundational models. Because the people who were using foundational model, just the raw approach of just using the foundational model and get an answer was like 82% accurate. And the people, just the raw, like, and then it went from 82 to 82.5, 83, 84 might be the winner, something like that. And the people who are not using a foundational model, but just the raw text and just training based on that, the best accuracy was like 72%. And the winner might be between like 70 or 72, like much below the foundational model. So that's where I was like seeing like, wow, transfer learning is like changing the game. So the bigger and bigger, the better foundational models you make. And that's what happened, right? Like they said, well, what if we just throw more data at it? You have a good architecture, like they didn't use the CNM. They used we didn't talk about the transformer, but transformer was just one of the architectures. So they said, let's just forget about it. Like, earlier, we used to think about deep learning architectures and all. And at some point, people said, let's just take this architecture. Let's not make any change. Just keep throwing more and more data at it and get bigger and bigger foundational model. And then we started getting GPT-3s and GPT-4s. And then
Well,
it's just the size of the model.
Girish has this video up on YouTube. You guys should go check it out, where it actually really highlights how NLP, natural language processing, works and how GPTs actually learn from an NLP perspective. Because that's like foundation, right? Like,
Absolutely. I totally know that I made a jump from computer vision to language and we didn't give
you
enough
went
details. Maybe
way too fast.
Yeah,
But
maybe you could have.
NLP, yeah,
Yeah,
NLP is really interesting. We don't have to go deep into it, but NLP,
yeah,
like, I think people should just go check out the YouTube. They should actually go, and Girish, we can put the link in somewhere
absolutely.
here that'll share
Yeah.
what NLP actually was and how it was created, because it's foundationally really important to all of this.
Yeah, and the NLP is natural language, right? So from vision, we are going to the language very quickly. But maybe, and yeah, I'll send the link, and maybe at some point we invite some guest and go a little deep and geek out a little bit more into that too. But yeah, then there was the Gen AI, right? Like then that's it. Like you can build foundational models not just for text, like GPTs, but for some specific structured data, for speech, signals, images, you name it.
AI before you
Mhm.
can get there. And general
That's true.
generative AI is a ways off.
And this shows the journey, right? Like where this is a continuum of our modeling, where initially we started with some business rules. Like people came up with their business rules on their own, and we used statistics and the p value. Remember, we talked about the p value on tossing the coin.
Last episode.
Yeah. And then we proved or disproved some business rules. And then we said, well, based on that, we said, well, why don't we just throw in the whole data and let the traditional statistical approaches and machine learning approaches figure equations out on their own. And then we talked about ensemble learning, where we said, well, each approach is good at one. So what if we mix these approaches, like the Netflix challenge, and then a combined approach, which is getting less and less interpretable? Like one machine learning model is clear to understand, but now you add 5 machine learning models and take an average of their output or something. Now it's slightly getting less and less interpretable, but better, right? Like, so that is the one that won the Netflix challenge. So it's getting better. Neural network is further down on that. Like, it's getting even less interpretable now, but even better at performing. And then LLMs take it like foundational models. It's trained on some data like in a completely different context. You're bringing it in, even less interpretable, right? And even more like even higher performing.
This was govai.fm. Connect with us on LinkedIn, suggest a guest, and stay tuned for real stories from AI in action.